And hello, everybody, and thank you for taking the time to attend today. So I hope everything is working with my microphone and video. And if so, I guess I can go ahead and share my screen here. Let's see. Good. So I assume if Felix doesn't start yelling at me that everything is working just fine, and then I will just proceed and I will talk. Okay, so yeah, hello everybody. My name is Nolan, and I'm a PhD student at ETH Zurich, shown up here. And I'm in the Optical Materials Engineering Laboratory, which we have up here on the top right. And today I'm going to talk about optical Fourier surfaces. And I think in contrast to some of the other talks, I'm going to focus less on how we use the nanofraser itself, and more how we can take what we make with the nanofraser, namely these really nice wavy surfaces, and how those will actually turn out to be very useful in the optical domain. And for those of you that have attended the thermoprobe workshop the past 2 years, you would have seen me present previous more preliminary versions of this work. And as Felix kind of alluded to, I'm finally very happy to know that the work will be published. Unfortunately, it's not out yet. It was just accepted a few weeks ago, but hopefully in the next week or two, the paper should be out, and then you're obviously welcome to go and read it. And until then, it's also on archive. So if you really have some burning stuff to look at, you can check it out. Okay, enough with the introduction. So the topic today will be on what we call optical Fourier surfaces. And so our story actually starts, a long time ago. Basically, as long as humans have been around, we've been trying to manipulate light through various means. And funny enough, this lens on the left is from ancient civilizations, but if we fast forward till now, modern times, we really haven't changed that much. We're still doing the same thing. And of course, these two lenses that I show here are very different. But actually, despite all these differences, they do have something in common. And that is that their function and performance, so what they do and how well they do it, is determined by the surface profile. And of course, nowadays, in contrast to some guy polishing a piece of glass, this relies on complex nanostructured surfaces. And this metasurface lens, which you see on the right here, this actually belongs to a very general class of optical components, and these are known as diffractive optics. And this is, of course, what we're going to be talking about today. So then the question is, okay, what are these diffractive optics and how do they work? So if we take the simple example that most people know of a diffraction grating, then we can understand. But first, if we just consider a flat interface, so for example, what we have in the case of a mirror, and if we shine light on this interface shown here, what we know from most of our basic optics education is that the angle of incidence will equal the angle of reflection. And this you can go test in your bathroom mirror basically in the morning. Another way to think about this is what we can say is that actually the in-plane momentum of the input and the output light is conserved upon reflection. And this in-plane momentum is a concept with which we can very handily understand diffractive optics. So now, if we take a periodically structured interface, so again, air and silver, and this periodically structured interface is a diffraction grating, and it looks like this. So instead of having this flat surface, we now have some periodic structure with a period given by this parameter lambda. And if we shine light on such a surface, part of that light will reflect, similar to what we had in this case on the left with the mirror. But in addition to that, what we can also say is that this diffraction grating provides in-plane momentum upon diffraction of the light from the grating. And this in-plane momentum, we can assign a value given by 2 pi over the periodicity. And the way that we can think about the operation of this is that this diffraction grating provides this in-plane momentum to the input light, such that when the light diffracts and leaves the grating, you simply can sum these two vectors, and this will determine your resultant in-plane momentum of the outgoing photon. And what this really means is that this outgoing light leaves at a different angle. And of course, this grating can also subtract momentum just as easily as it can add it, and this basically gives you your +1 and -1 diffraction orders. And this of course is dependent on the wavelength, so this is where you get your angular dispersion in the grating. And this situation here is kind of the classical one that we know from many spectrometers, where we're trying to disperse our input light, to its individual components. But another thing diffraction gratings can do, which is especially important in modern times, is it can couple input light to bound electromagnetic modes. And this is, of course, important in many integrated photonic devices. And so, for example, if we choose surface plasma polaritons and we design our grating correctly, what we can do is we can couple this input light to this bound mode, which will then propagate away along the surface. And of course, this very simple model here is nice to develop our basic understanding of how these components function. But as is normally the case, the full treatment is much more complex, and it's based on wave interference and optical fields. And so, is there a more general framework we can use to understand how these diffractive optics work? And the answer, of course, yes. And this is the what we call the wavy world of Fourier optics. And so what Fourier optics does is it basically studies optics and optical phenomena using Fourier mathematics, namely the Fourier transform. And what this allows us to do is it allows us to take very complex problems and decompose it to a simple sum of sinusoidal waves. So for example, if we revisit our diffraction grading that we had on the previous slide, and we write down the Fourier transform, or more precisely the inverse Fourier transform, what this equation tells us is that for any arbitrarily wavy surface profile, we can relate that to its so-called spatial Fourier spectrum. And this wavy surface profile exists in real space, and the spatial Fourier spectrum exists in frequency space. And it's actually here in frequency space that we can understand and furthermore specifically design the diffractive properties of our surface to do what we want. And this theory and this mathematics is very handy, and it's also very beautiful. And we can use this to make a great stride in how we understand and design these components. But the problem is that in reality, in the real world, we have this very ugly limitation that actually real gratings are not wavy, but typically they take on these square profiles, which you see here. And what this means in terms of the Fourier spectrum is that this is actually not a square profile, at least in terms of what the photons see when they hit this grating, but it's actually a profile composed of a large number of sinusoidal waves. And typically, if you read in a lot of textbooks or papers, people will talk about these gratings as if they have a single periodicity. And while in some applications that might be a sufficient approximation, it's actually not true. And what this wavy surface profile looks like, if again we look in frequency space, is that actually, we have some particular Fourier spectrum where each peak here is associated to a wave that we have in the surface. And so ultimately, these square gratings, they have two problems that arise from this. The first is that in addition to the spatial frequency that we care about, we have many unwanted spatial frequencies. So, as you can see here. And furthermore, you can't freely add spatial frequencies because, again, this would require being able to control the wavy profile of your surface. And actually what this does is this limits the function that you can achieve with diffractive optics because you can't kind of include the components that you want. And so ultimately, this is a limitation that is, making the life of researchers difficult when they try to design diffractive optics. But of course, researchers are clever. So how have they approached this problem in the past? And this is actually a field of its own, and there's not enough time to go into all the details, but basically we can call this Fourier spectrum engineering of diffractive optics. And the goal of what people are trying to do here is, as we learned previously, is to control the spatial Fourier spectrum of some particular surface pattern. And if you could do that, it would allow for high performance diffractive optics with advanced functionalities. But of course, there is limited control with traditional fabrication methods. So researchers have tried to do this using various approaches. And again, just to show some notable modern examples, what people have tried to do is to arrange their patterns in some particularly clever way on the surface, shown here with a quasi-periodic pattern. People have also implemented complex process cycles where you have multiple depth levels for multiple etching steps. Or simply you can do both, and some infinite combination of all these complexities as shown here, where they had some pattern and they had these different depth levels. And the thing that we notice is that the design and especially the fabrication of these surfaces is quickly getting more and more complex, but it still doesn't really solve the problem that we're trying to tackle, and that is that of controlling the Fourier spectrum. And in order to do this, simply speaking, we would just need to be able to make wavy surfaces. So the way that we approach this problem is with a solution that we are proposing called optical Fourier surfaces. And the way that we do this is we start with the simple analytical design, which comes directly from Fourier mathematics. And with the nanofraser, we take that design, which is then converted to a grayscale bitmap, and we simply print that mathematical profile, so to speak, into the surface with the nanofraser shown here. And so, we pattern the surface with this 3D profile that we care about, and the way that we go about transferring it to optical materials, so in this case, silver, what I'll be talking about today primarily, is we use a thermal evaporator. So we evaporate the silver such that it fills up the profile. Then we take glue, we stick it on the back of the silver, and we just simply pull it out of this so-called template. And this is called template stripping. This is a common process in a lot of optical devices. And just for the NanoFraser users that are attending, for resist, we use this somewhat more standard electron beam lithography resist, PMMA MA, more for historical reasons. It was convenient at the beginning of the project and it wasn't broken, so I didn't try to fix it. But anyways, this is what we're using, and these cantilevers called these MBS are very good for these patterns. And so once we go through this process flow, the final thing that comes out are these wavy diffractive optical surfaces, which you see here in silver. And of course, it nicely reproduces what we have on the left. And not only do the surfaces look very pretty, but actually when we go ahead and we quantify the error on such a profile, we see that we can achieve these really low values in the final optical material. So that's really great and really exciting for us. And then the question is, now that we can make these surfaces, how do we go about optically characterizing them? And the way that we do that are we use something called surface plasmon polaritons. And just to get everybody on the same page, we'll quickly look at what those are. And these surface plasmon polaritons, simply speaking, are a surface-bound electromagnetic wave that is part photonic, part electronic in character, kind of illustrated here. And these surface plasmon polaritons can be described by their dispersion relation, which for a flat surface, the equation is shown here, and that is graphically depicted below, and showing how they compare to photons, which access the blue states here. And so then what we're going to do with these surface plasmons is we're going to introduce a structured surface, so our optical Fourier surfaces, we're going to shine light on them such that these photons couple to these SPPs, and this is what we're basically going to measure, so as I showed in the previous slide here. And what this does is it gives us just a really simple and clean system with which we can study these gratings, as you'll see when the data comes, and then we can learn a lot about what these surfaces are doing. And so then the question is, how do we actually measure such a phenomenon, what I showed here? And so if we look at this dispersion relation, which I had plotted on the previous slide, this is for a flat surface. And the one thing that we immediately notice is that at a particular value of photon energy, these surface plasmon polaritons shown here have a larger value of in-plane momentum than the corresponding photon at the same energy. And what this really means is that these two optical modes have a momentum mismatch between the two, meaning that they are not able to couple to one another. Now, when we introduce a grating surface, what this grating actually does, or what we learned previously, is that this grating provides or subtracts the amount of necessary momentum to couple these two states together. And then, so basically what we can say this does is this creates a photon SPP coupling channel. The second thing that these gratings do is at this very specific condition where the grating momenta spans the counterpropagating plasmonic wave vectors, these two counterpropagating modes become coupled. And what actually happens is that they become strongly coupled together, and then this opens up a band gap in the dispersion. And these coupling channels and these band gaps, these are the features that we are going to use to monitor the effect that our surfaces are having. So how do we achieve this in an optical experiment? We do what's called a reflection measurement. So basically we shine light on our surfaces and we look at what comes back. And this reflection measurement contains all wavelengths in the visible spectrum, it's broadband, and it contains some particular range of angles given by our microscope objective. And if we look on the left here, we see that within this entire physical situation, we can access some particular window based on the spectrum that we're sending in and based on the angles that we can collect in such an experiment. And that's what we're going to monitor with our optical data. And so how does it look? Well, if we start with the sine wave surface that I showed previously, we see that in addition to this nice picture, that the surface has this nicely sinusoidal profile, where that's what this dark blue line is. And this has a single spatial frequency according to its Fourier spectrum, shown in the inset here. And what I showed on the previous slide is that for a single sine wave, this is what we will be trying to measure, namely these two bands that fall within our optical window. And when we look at the data, this is indeed what we see. And so this data here, this is plotting the photon energy as a function of the in-plane wave vector, so what we've discussed previously. And this is a reflection measurement. So it's looking at how much light is reflected. So where it's dark here, what this means is that it acts like a mirror, 100% of the light comes back. And where you see these kind of orange bands, this means that some light is not reflected and therefore it's going somewhere else. And on the left is our experimental data, and on the right is our model. And what this shows is that these bands, these are actually these coupling events here, where these photons are coupling to surface plasmon polaritons. And that's nicely what we see here. And this is great. So it shows obviously that it works and that we can understand with these simple pictures how this works. And furthermore, this sine wave now is our building block. So this is what we start with. And what we can do is we can freely add sinusoids as we want to achieve some desired optical response. And this is what we're going to be doing for the rest of the presentation. And so just as the next step in complexity, what one could think of doing is just simply adding an additional spatial frequency to open up another coupling channel. And this is what we do with this surface here. And of course, we see here that you have some profile, which is now containing these two spatial frequencies, and we can nicely transfer to the surface. And when we look at the optical data, even though the surface might start to look quite complex, it simply follows the rules that we've established before, where we open up an additional coupling channel, now one for each spatial frequency. And of course, we're not limited at any point to 2 sine waves or any number, and we can continue this game as long as we would like. And just to show a particularly different example, if we add 2 more spatial frequencies shown here, G2 and G3, and they are sufficiently high, what they can do is they can open up band gaps in the dispersion. And this is indeed what we see in this optical data. So these band gaps I mentioned previously, we are now able to selectively introduce them where we want in terms of the energy and the dispersion. And again, the take-home message here is that if you were to try to guess just based on the real space profile and all its complexity what was going on, it would be an impossible task. But if we just decompose it simply to its Fourier components, we can understand and we can design these surfaces very well. And at this point, you may be wondering how these wavy surfaces compare to what people have been doing with more traditional methods. And just to show an example, so if we take these analytical functions from the previous slide and we convert them to a 2-level profile with a thresholding procedure, and just to show that this is not some random approach, this is actually being used in very modern laser designs, and this one here from Jerome Feist's group at ETH, a notable laser group, this is how they actually make some of their complex diffractive surfaces. Then when we take this thresholded profile, we can fabricate it with standard techniques, so electron beam lithography and etching. And in the end, this is how it comes out. So on the left are the profiles I showed you previously, and on the right are their so-called binarized versions. And what you see is that essentially you lose a lot of the information that is going into these wavy profiles. And furthermore, when we look at the optical data, I think we very clearly see that this optical data becomes very corrupted, from these square profiles and with all of their unwanted complexity that they introduce. And so what this shows us is that with our Fourier surfaces, we can precisely manipulate electromagnetic signals in some way that we would like to take advantage of. And we can do this relatively easily based on Fourier mathematics. And now that we can just simply do this, the question is, what else can we do? And one thing we can do is with these stop bands, which are important for many applications, we have free control over the width of these stop bands. So if we take this 2-component function here, where the amplitude of the second Fourier component is responsible for the width of the stop band, and we tune this amplitude from over some range, 0 to 25 nanometers, we see over here a GIF of how this profile evolves. And so as the amplitude of the second component grows, you can see that this function is changing correspondingly. And what's really cool to see is that, again, when we look at the optical data, it follows exactly these expectations from this very simple Fourier mathematics. And what this shows is that we have a completely independent tuning knob over the width of such a stop band and also its position that is only possible when you can construct a profile such as this. And of course, there are many interesting phenomena that we can observe, and another particular one is that of symmetry and how the phase of these functions has an effect. And so if we take a similar function where now we sweep through the phase, what we see is kind of a different behavior where this function changes from different cases of asymmetry to symmetry and back. And again, if we look at the optical data, it's very striking to see how the photons follow these behavior. And simply speaking, what we see here is that the magnitude of the absorption, shown with the colors, is shifting from left to right depending on the symmetry of the grating. And we can also, these little gaps that are opening up down here, these are so-called dark modes or symmetry protected bound states in the continuum. And we have free control over where these dark modes exist or do not exist. And again, these are things that people like to make use of for many applications of these surfaces. And until now, everything I've shown you has been done with sine waves along one direction of the surface, so namely x. But of course, it's no surprise that surfaces are 2D. And so we can extend these capabilities now in, sort of all in-plane directions along the surface. And what I had told you previously is that for a sine wave depicted here with these little sticks, that this is what we're measuring. But in reality, the total picture looks like this, where a surface has 2 directions, x and y, and in k-space, this of course traces out the kx, ky plane. And this SPP dispersion actually becomes a cone when you're not looking at this slice. And when you look at this from the top, if you have, again, a single sine wave, what it will do is it will diffract a circle into your experimental window rather than these lines here. And this is at a fixed value of energy. So we just fix our energy with monochromatic light. We take a slice, and this is now what we're monitoring to get our 2D information about how these surfaces diffract. And when we add an additional Fourier component rotated at some in-plane angle theta to the first one, then what we see is that we will see an additional pair of circles, which now correspond to this additional sine wave. And when we take this concept and we go ahead and we implement it with a real surface, so what we have here is a silver surface composed of two sine waves that are rotated 10 degrees relative to each other. And the first interesting thing is that to some degree, this does look like a one-dimensional grating, but if you look close, of course, you see that there are these elements of intricacy and complexity that come from the fact that we're actually superimposing two sinusoidal functions. And again, what's very satisfying is we see that the data comes out sort of exactly as one would expect from Fourier mathematics. And so again, this data is reflecting this cartoon here, and this is a reflection measurement. And so we nicely see our two pairs of circles that come from the two Fourier components. And of course, we are now free to choose any in-plane direction along the surface with which we want the sine wave to go. And if we take the same one that we have here, but we simply rotate that second sine wave 40 degrees relative to the first rather than 10, of course, the profile in real space changes quite a bit. But in K-space, simply all that happens is this second pair of circles, they just rotate correspondingly as we would expect from these angles. And again, these dashed lines, these are the expected positions from analytical calculations, and we see that they nicely agree with the data. And now that we have such symmetry along a surface, such control of these sine waves along a surface, the question would be, well, are there some particularly interesting symmetries that we can look at? And one particular area that I find quite interesting is that of higher rotational symmetry and how that's manifested. And so if we take three sine waves similar to before and we rotate them 60 degrees relative to one another, what we end up with is actually a hexagonal crystal pattern, which many of us know either from plasmonic Hall arrays or maybe even solid state physics. And this hexagonal crystal, as you see here, even though it's defined with smooth sinusoidal functions, it looks pretty standard and it has the six-fold rotational symmetry. And of course, we can transfer that to a metal surface. And again, when we measure the optical properties of the surface, we nicely see that this diffractive profile also has this six-fold rotational symmetry. And again, these dashed lines are calculations of what we would expect, and we see a very nice agreement between the two. But what's actually quite interesting is that this six-fold rotational symmetry is the highest that you can have for a so-called periodic or crystalline structure. And that would raise the question of, can you increase the rotational symmetry of such a surface structure? And we can actually very simply, based on just the sinusoidal addition, you can sort of freely choose any number of sine waves. And if you orient them in the correct way relative to each other, then you can simply just add more and more, and you can freely increase the rotational symmetry of your surface. But what's really interesting is that when you do this beyond the six-fold rotational symmetry case, you actually end up with something, if infinitely extended, that's called a quasi-crystal. And these quasi-crystals are said to be quasi-periodic. And what this means is that they don't have translational symmetry. So if you try to move this structure in any particular direction, it will not look the same as it did before the translation. But it has this really high rotational symmetry. And this is just somehow a fundamental trade-off of nature and how these structures will assemble on a surface. And of course, we can transfer this to an optical material. And as you should probably expect, we see that this high rotational symmetry exhibited in the real space surface profile is transferred to the optical properties. And again, we see a very nice agreement between this very seemingly complex pattern and what we can calculate from the simple Fourier mathematics. And of course, this gets a little bit more abstract at this point, but I think this would also raise the question of basically, are these surfaces actually useful, or can we do something useful with them? And so if we take a look at that, first we can start with what I had told you at the beginning, that until now people had been doing everything with these square gratings, and that these square gratings have these problems associated with them. And then, of course, we learned that now we have these Fourier surfaces, which we could freely implement, and we don't have these limitations anymore. So we don't have these unwanted frequencies, and we can freely add the spatial frequencies that we would desire. And so this would imply that we should be able to do two things, that these gratings should perform with high efficiency, And we should be able to now implement a new functionality to solve an existing problem that wasn't possible previously. And if we start with these high efficiency diffraction gratings, I show a schematic here on the left, and unfortunately, due to time constraints, I don't have enough time here to go into all the details of the optical measurement, but if you're interested, I have a backup slide I can happily show you after. But basically what we're going to do is we're going to shine light on this grating, shown here with K incident, and as we learned before, some light will reflect and some will diffract to these orders, and we will capture these orders and we will directly measure how much intensity is in each of these orders relative to the input beam. And with this, we can quantify our diffraction efficiency. And of course, two just small disclaimers is that because we take a reference also on the silver surface, it doesn't account for silver reflection losses, which aren't high, it's just a few percent. But of course, this is important if we really want to quantify these things. And as always, there's some fluctuation in the values that we measure. And so if we take a grating, sinusoidal, like we have here on the left, and we make this actual grating, what we see is that these surfaces actually exhibit very high diffraction efficiency. And so we'll go through this slowly. So on top is the profile. And the first thing you also might notice for those nanofraser users out there is that this grating has an amplitude or a depth, more precisely, of 200 nanometers. And actually, we were very excited when we were able to achieve that because this is something we were trying to do, make these high efficiency gratings, which required these deep profiles. And it was really actually uncertain if we would be able to. So this is very promising to see that we can do this just with direct patterning. And then if we look at the data, again, with this color code, what we have is that this +1 diffraction order is the red curve, the -1 is the green curve, and if we sum those two up, that's the blue curve here. And what we see is that relative to our incident light, nearly half of the light is sent to the left and half to the right, which I think we would expect based on symmetry. And of course, because this case is symmetric, if we sum the total intensity that is diffracted, we arrive at this blue curve here. And we see that nearly all of the light is diffracted from the grating into these orders that we care about. And this is quite nice, but the thing is that for many applications, what people actually want to do is to send all of their light into just one particular order, so only into this +1 order here. And to do this, of course, you need to break the symmetry of your structure. And for those of you that know a bit about optics and gratings, people do this with these so-called blaze gratings. And a way that we can do this very simply with these sine waves is we can simply add an additional spatial frequency, so just 2 sine waves here. And if we choose the phase correctly between these two components, we can arise at this asymmetric case here, which actually is somewhat of an approximation to a blaze grating, as we see here. And what's very satisfying to see is that when we track the intensity of the diffracted light into these particular orders, what we see is that we can actually design these gratings such that nearly all of the incident light is diffracted to the +1 order that we care about. So it behaves really like a very, very high quality blaze grating. And that was very nice to see. And again, these high efficiency numbers, this is only possible with these really deep structures here. So we weren't sure, but we were very happy that we were able to achieve that. So that's pretty cool. And of course, finally, now that we can do these efficient gratings, the question would be, can we implement some new functionality, ideally to solve a problem that has existed? And this particular problem arises when we look at multi-wavelength coupling, which of course is important for many applications. One I choose to show here is a multicolor integrated hologram on chip. And of course, many modern optical devices are becoming smaller and smaller and being integrated on a chip. And what this one did is it made a computer-generated hologram out of color with red, green, and blue, all in a single thin waveguide, depicted with the cross-section here. And what you notice is that when they have to couple 3 different colors into such a waveguide, because these gratings are dispersive elements depending on their wavelength and the periodicity of the grating, what you actually have to do is you have to couple these colors at very different angles. And the whole sort of selling point of what these guys did in their paper was to make this miniaturized integrated waveguide optical device. But as you can see, you can't actually really make it that small simply because, you know, you have to have these 3 different lasers coming in at 3 angles on your table rather than from the same optical fiber, for example. And so this angular dependence is a limitation that is frustrating, you know, ultimately the miniaturization of such devices. And so the question is, how can we eliminate this? And of course, we can sketch how we would expect this to behave. So you have some surface profile, which is being illuminated with 3 different colors at normal incidence. And we want that surface to couple all 3 colors coming from the same angle. And it should be no surprise that in the Fourier mathematics picture, we can do this very simply by including one spatial frequency corresponding to each color that we want to couple. And we can take this 3-component function, and of course we can implement it. And again, you know, we have some complex looking surface that we can only do with the nanofraser. And we can transfer this, of course, again to silver. And the surface, when we take it and we shine light on it, what we very nicely see is that this surface is able to simultaneously couple the 3 colors we want, red, green, and blue, shown here nicely with this optical data and their 3 corresponding peaks. And the take-home message there is not only that we made such a surface that can couple multiple wavelengths, but it's really a demonstration of how this approach not only is very simple, but it's also very powerful, that you can really use it to sort of precisely solve these diffractive problems that you may want to do. And the final thing to show is that depending on what you want to use these surfaces for, you may require that you're able to transfer these profiles into a number of different materials. And so until now, everything that I've shown has been with this templating process to transfer these materials to silver. But we've also shown that using templating, we can transfer it to dielectric materials, so such as titanium dioxide, this high index dielectric used for many optical applications. Or we can also use etching processes to transfer the patterns to semiconductors, which would then, you know, we use as the substrate. So for example, silicon nitride or silicon shown here. And what's really nice about this one in silicon is it really shows that, you know, not only can we pattern these very beautiful and these very complex surfaces, but we can actually nicely transfer those patterns to a number of different materials, depending on what people want to do. So with that, already I'm at the conclusion. And so as we've seen today, I think the first takeaway is that everything that we've shown, it really starts with the nanofraser, and everything that I've shown is really only possible by using the nanofraser. And with this technology, we have introduced the concept of Fourier surfaces, and of course they're based on this very simple analytical design. And with this precise surface patterning of the nanofraser, we can achieve that, and we can transfer these patterns with very high quality to a number of relevant materials, specifically optical materials in our case. And when we take these surfaces that we made and we use them in the fashion of a diffractive optical element, what we see is that we can use these surfaces to generate improved diffractive optics, nicely shown here when we compare to this previous state of the art. And finally, of course, this shows that, you know, this is only just the beginning, right? I mean, there's actually many exciting new ideas and possibilities that are coming out of this technology and this way of thinking. And of course, you know, myself, I'm thinking very much of the optical implications and what we can do with that. But I think the more general point is that this 3D patterning of the nanofraser actually is very cool and can open up exciting possibilities in many different fields. So my closing remark there would be that if you don't have one of these nanofrasers, you should definitely go get one, because this is basically what a lot of people are using to make very cool stuff. So it's a really neat tool. And with that being said, of course, this work was not done just by myself. It's actually a whole team of very talented people. So David Norris, he's my professor, my supervisor, shown here in this picture. Raphael Brechtbuehler, my 2 previous Dutch master's interns, Cornel and Sander. And from Swiss Litho, Heidelberg Instruments specifically, Martin Spieser. He was there from the very beginning of the project, you know, providing very helpful support. And in more recent times, now that he's no longer there, I'm working a lot together with Sammy on this stuff. And I think it's really actually important to say that a lot of what I showed here would not have been possible without the inputs of Martin and Sammy and all of their, you know, time that they spent on this. So very thankful for that. And also Sammy's a very good fisherman. I think that's a point we can make here. And also finally, another couple Dutch collaborators, Boris and Freddie, who also were very instrumental in this project here. And beyond the co-authors of the paper, of course, within this community, there's many people that I would like to thank. First and foremost, Felix. You know, back when I was a master's student, I actually interviewed with him when I was trying to get an internship. And so he was sort of my first contact to this whole community. And he sent me over to Urs and Armin at IBM, where actually I did my internship. I got exposed to the technology, and, you know, they supervised me there, and also they continue to support me to this day. So I'm very thankful for that. And of course, there's not enough space on the slide to thank everybody that I should at Heidelberg Instruments, Nano Swiss Litho, and the IBM community. So thank you for everybody for all that you've done. So with that, I will stop talking now, and I would be happy to take your questions.